I'll start. Hello, everyone. I'm Hande McGinty, and thank you for inviting me to this roundtable. I'm very happy to be part of it. I will briefly tell you a little bit about my background. Currently, I'm an assistant professor at the Department of Computer Science at Kansas State University. I'm a computer scientist by all my degrees, but I worked in interdisciplinary teams for over 20 years now. And before joining Kansas State, I was working at Ohio University with the USDA, and we worked on building an ontology backend for FDC, Food Data Central, which is one of the biggest databases and most used databases for food. Before I was working with the USDA, I was working actually in industry for a company called Collaborative Drug Discovery, CDD. And before joining CDD, and one of the reasons why I joined CDD was because at the University of Miami, I was finishing up my PhD building some drug discovery and bioinformatics related ontologies, and CDD started using them in their products. So it was a natural way for me to kind of continue working on that and move on to the next project that I have. Today, I don't think I need to convince this group that we can do better than just statistical analysis, right? So with statistical analysis, sometimes we just get results that we already know, which is not really useful all the time. And then there's the other end where people are using AI and think things like, oh, we just put in the data and it works. Nobody knows how it works, but it just works. So it's not something we want to say as scientists. We want to do better than that. So ontologies and knowledge graphs are great ways to make sure that we don't say something like that. Another reason why we use ontologies is to put together data that's seemingly disconnected, but actually very much connected, right? One of the big data sets in a way that I started working on were about global food systems data. As you see here, it has a number of different pieces that float around in different databases within the government, outside the government, in the industry, and so on and so forth. But before that, the reason why I kind of had to come up with a systematic way of developing ontologies was because I was working on 3 nationwide projects. They were all NIH projects. Thank you very much for the funding. And it was around the world and within the country, data centers building, generating data. And our job as the data center was to connect them all. It was a very daunting task, as you might imagine. And of course, when we think in computer science, when we want to connect things, the first thing comes into mind as a computer science construct or a mathematical construct is a graph. When you dump everything on a graph, though, my favorite scientific term appears, the hairball graph, where you cannot really see what's going on and you don't really know why we're seeing all of this all at once. So what is a good way to describe these concepts and relationships? There are many ways that we've used over the years. As computers and their capabilities progress, we changed our ways and improved our ways. Right now, I'm operating over here where we see description logics. And of course, we cannot forget the databases that we've used and generated years and years ago, and reuse what we have so that we're not wasting time on reinventing the wheel. Uh, Again, I don't think I need to sell you all why we need to build ontologies, but I'll go over it anyway. We want to limit complexity. And I know all the data sets that we're working on is complex, but if we can identify things that really connect them to one another and align the domain experts' knowledge with the machine's knowledge and vocabulary so that we can use better analysis methods using artificial intelligence, and we can organize the data into knowledge, and of course, create knowledge graphs for inference and better analysis using AI, which we started using the term neurosymbolic AI for, right? Part of that. Okay, so one of the latest questions that I focused on at the USDA was, how can we represent chemical components in food products better? I know Matthew already went over a couple of different ways to organize them and show them and why they're important. And I will talk a little bit about how they are important and why they're very much connected to health and disease and drugs and food and agriculture. So that's why we chose to kind of focus on a very limited data set at the USDA and really try and identify how we can represent chemical composition components of food products better using ontologies. So of course, I don't have to tell you that it's an interest for all kinds of different health organizations. And of course, interests of researchers. Matthew, again, talked a little bit about ISCL. There are different efforts like periodic table of foods. And of course, there are a number of other ontology efforts that are going on that are connecting or trying to connect all the different parts of food and agricultural research. Okay, so when we start building ontologies, we really start building FAIR data from the start. And once we have an ontological framework or a backend in our systems, then we can generate new and incoming data in a fair way too. And of course, the Q part stands for quality in the title, because quality, as we've seen, especially in artificial intelligence research, right, is a very big and important part of FAIR data that I don't think is gaining the attention that it needs. So that's also very important to keep in mind. How do we create quality data and how do we do it systematically? So as I mentioned, through my work on the national projects and with the USDA, I decided that if we do not follow a systematic approach in building these ontologies and knowledge graphs, it all goes out of hand very quickly. So what are my steps? The first step and the second step, what I call sub-language analysis and unstructured interview, just for the sake of it, is really trying to understand what your data is telling you and really working with the domain experts to understand it. For the drug discovery and bioinformatics research that I did, I had to put together, for example, the different bioassays that the different data centers were running and generating data from, and also the drug target proteins that were being studied in different centers around the world. Of course, for the USDA's Food Data Central, we focused on Foundation Foods dataset for looking at our dataset. And the first step for me in all of these was to really try and understand what the data is saying, what are different aspects of data, and what are different aspects of data that I need to take into consideration building the ontology. The third step is really understanding that you are not alone and you are not creating all of this by yourself. Thank you. I think Kai is here, and I adopted this slide from his slides because he and I agree that OBO Foundry is a great way to reuse some of these ontologies and efforts and really take into consideration before you start going on your own and trying to build vocabulary all alone. I am an active member of the OBO Operations Committee and OBO Foundry governance team. And I think it's great that there is so much effort in building quality data, vocabularies and ontologies using the OBO Foundry principles. I'm not going to go over them. It's online. You can probably look it up yourselves if you're interested in building this. But there are a number of principles that OBO Foundry and the ontology builders at the OBO Foundry use to ensure that the vocabularies they build are not only fair but also of quality, so that it can be reused over and over by many different projects. So the next step then is to really do the knowledge modeling. So this is a work that we're trying to publish right now about how we can describe food product. It's slightly different than how Foodon did, and it's a little bit more systematic in how the different components connect to one another. as you might have noticed. I'm going to talk, as I mentioned today, a little bit more about the nutrient components, the chemical composition components of food, and how we kind of looked at that as a connecting point for food, health, disease, bioassays, and drugs and agriculture. So the question that we tried to answer was, how can we represent chemical composition components better? And I know Matthew already showed a slide where he was mentioning CDNO. And CDNO was one of our resources that we reused and mapped our data. But we also used USDA's own nutrient components to create our own classification. But that's the beauty of this methodology that I am talking about today, that I call KNARM. And let me tell you a little bit of a story here. KNARM, KNARM, is not a very great acronym. Then I'm trying to reinvent the methodology as karma, but we'll see which one sticks. And anyway, so here in this, with this methodology, whether you want to call it NARM or karma, whichever sticks, is that you can reuse previous classifications, previous vocabulary, and map it to your own applicational needs and query needs and your audience's needs and so on and so forth. And that's the beauty of following a systematic approach in building ontology, so that you can really manage all those different things. And this is just part of it. Okay, so once you have a way to model your knowledge, then of course you really want to, before you go on and really start full length ontology building, you really want to make sure that all the different components you're taking into consideration is answering the complex questions that you're trying to answer. And one of the great things about knowledge graphs or ontologies are that they can connect seemingly disconnected data sets, such as diseases and food and nutrient components, which are basically chemicals. So this process is, of course, it's based on the data that you're using, and you need to make sure that you're answering questions for all the different types of data that you're using and trying to connect. Here is another example from a previous data set that I used that was also connecting the bioassays to gene ontology components to disease to drug target proteins to the links projects related protein and gene information. All right. So once we have our knowledge modeled and everything in place, now the computational heavy lifting starts. And I'm a hands-on, ontology builder. I've been doing it for a while now. I really believe in sustainable data storage. I also believe in working with the domain experts and their, tools of preference. But I think that creating a database or reusing an existing database is essential. So when I started working with the USDA already started using a graph database, but we did a number of different steps to clean it up and make it more user-friendly so that we can have a better and more pleasant viewing experience. Here you can see that the orange dots here are representing the different samples that you can find in the USDA's data, Foundation Foods data sets, and then the gray ones are showing the nutritional components. And here, the little green nodes here show the different ontology mappings available currently at the FDC. And of course, we also started integration of ontology on Neo4j at the USDA as well. So once we have that, and once we have everything that we need in the backend database, then we can start building the ontology. Again, following a systematic approach here. And I'm sorry, this figure is too big, but you know, trying to show the full picture here, that we start with generating the vocabularies that we build. And we can then create modules of information and reuse the external ontologies that we want to reuse and create different views of the data that we have in knowledge graph format. Um, with this kind of a modular architecture and the systematic build, we can easily map our vocabulary to upper ontologies like BFO, but we will still maintain the integrity and consistency of our own vocabulary sets and our own data sets. And kind of my favorite analogy, if you listened to me before, you know that is Lego pieces. You can use different Lego pieces from different sets to build your own little set and your own little design. Or you can use the different, you know, Lego pieces to build something completely, you know, additional to another set. So we can use this modular architecture to do just that. You can map to upper ontologies, or you can select pieces for a particular application that you're using. For example, some of the applications we used at collaborative drug discovery use only a couple of different modules from the ontologies I built as part of my dissertation. And that brings me to the ontology validation. Of course, the first step is ensuring that your complex questions can still be answered. All right, with all the different steps that you followed, all the different computational tools that you use didn't disturb the integrity of your modeling and your efforts. But I saw Larry was here too. I know he and I worked a little bit on this too. As I was mentioning, the ontologies I designed were used by collaborative drug discoveries by a Harmony annotator. And with these ontologies in the backend, or parts of the modules of the ontologies that I built in the backend, we were able to annotate some of these human readable text in machine readable format using the ontology terms that we generated. So that is exactly the kind of use case that comes into play when you're really using the ontology. Am I time? Okay. All right. Okay. And of course, you know, when you are trying to automate this process, you also see that you can use AI to really expedite this annotation and make sure that you are actually creating a pathway to better analysis using the axioms and formal logic. As we've seen this process going on, one of the things that we've seen was that the constant need to add new terms. Ontologies, by definition, are not final, right? They're always in motion. They always need updating. So one of the tools that we generated with Stanford and University of Miami at CDD while I was there was this tool we called OntoloBridge, where you can generate and request new terms on the fly as you're annotating your assays. But of course, the ultimate goal we have is creating scalable knowledge graphs. And as Matthew was talking about, you know, chemical composition component is key in this, right? Drugs have chemical composition components, pesticides, fertilizers, and foods, they all have chemical composition components. We see chemical composition components used in bioassays. We see drugs used in clinical trials, and, you know, everything can be connected to diseases through all of these different chemical composition components. So it's all very much connected, but it's important that we follow systematic methodologies such as KNARM that we can reuse over and over again, reuse existing efforts and vocabularies to make sure that we're not, we're helping AI systems to better analyze and minimize the bias that's going across different tools. And with that, I would like to thank all the funding agencies that helped me throughout this research, and all the teams, all the great teams that I worked with. I know USDA teammates are here, and I don't know if, I know Sia is here, who's also co-author on a paper with me, and a number of other people who helped me through this process. Thank you very much. And thank you for reminding me again. All right.